All right, I gave you some homework. Did you have any questions?
Can we have one more day before we take this quiz?
One day, I'll give you that. I mean, I'm fair about this. Convolution is a pain in the butt. There ain't nobody that can tell me it's easy. It takes time, a lot of time, especially when you're dealing with odd-looking functional forms. When you flip and shift to get the mathematical equation is not something that's obvious most of the time. Yeah, I'll give you one more day. I'll do it Wednesday. How's that? And then we'll go to Friday. Yeah.
Could you work like one of the parts of 2.29?
Absolutely. Okay, you're going to have to help me. I don't have it right here in front of me. Just tell me.
So you have...
Jeff, can you see all this stuff I want?
Dr. McKenzie, what was the part about Friday you said when you said something Friday?
We'll forego the quiz Friday if we do this Wednesday.
Okay.
But if you don't show up Friday, there's a sizable deficit, then we'll have a quiz. I'm fair.
Thank you, sir.
Not many people, you get a quiz anyway. All right. Well, what is it? Who's asking? Yeah.
So you have a LCI system, and the h of omega is 1 over j omega plus 3.
Oy vey. I didn't, that slipped through the cracks. That's something that has to do with a transfer function of frequency domain. We can do this one, but you are ill prepared to do it. I can show you it now if you want. I apologize for that. It did get, I took and cut and pasted stuff I had before. I'm sorry. Is there something else besides the j omega? Sorry. Some of you probably know how to do it, by the way. That's what's called Fourier transform. You've done all this stuff. Remember in circuits, whenever you had a derivative, you brought out a j omega, time derivative, right? So impedance of like an inductor is j omega L, capacitor is 1 over j omega C. That's what that j omega is. All right. Anyway, go ahead. More on convolution.
Then can you do the part of question 3 where it was e of negative t times...
Is it first function is what? Are there two functions?
It just says convolve where you have e of negative t multiplied by the convolution of...
What, is it a multiplier or convolution here?
There are two terms being convoluted.
Convolved.
Or convolved.
That's right. Now which problem is this, so everybody knows?
It was 3 on the...
yeah, number 3 of the special set. Yeah.
Yes.
Okay, go ahead. Give me as much as you can. Go ahead.
Okay. E to negative t, e base 2.
No, that's the pulse function. It's the pulse function with 2 of t, right? Or is it t minus 1 or something like that?
Just t for this.
Okay.
And then convolve with e base 2, t minus 1.
T minus 1. First, we have to look at what these pulse functions look like. Now, how many understand the pulse function is the same thing as a rect function? Everybody understand that? That's simply, the subscripts tells you the width, right? The pulse function. The point where it's 0 tells you the center point, doesn't it, class? So we take a look at P2 of t here and graph it. We go to minus 1, 1, this is versus time, and this is what it looks like. Are you with me? Everybody understand that? Now, take a look at that. That has a height of 1, right? It's got a width of 2, correct, class? When I multiply this by this, e to the minus t, I'm really just saying e to the minus t exists from minus 1 to 1, right? And 0, and then that function is 0 everywhere else. Does everybody understand that? Are you with me, class?
Can you say that?
Yes, if we take this and multiply it by e to the minus t, really we're saying we take and simply sketch e to the minus t and only have it non-zero between minus 1 and 1. That's all it does. It strips out those values. Do you understand, everyone? So I'll graph that as best I can. Below it, that's P2 of t. Now when we take P2 of t and multiply it by e to the minus t, it looks like this. Now it looks like this. value here is 1. And this is e to the minus t from here to here, and then it's 0 anywhere else. You all see that, class? How many do? With me? Well, you know what e to the minus t looks like, right? It starts, just think about this. If this is 0, right? 1, 2. If I talk about e to the minus t, what does it look like? Well, if I start right here at 0, it looks like this, just decaying, correct? Right? Go negative. Blowing up to infinity, isn't it, class? So now I get that snippet from minus 1 to 1. Got me? All right, now he wants to convolve that with this pulse function, p2 of t minus 1, right? What I'm going to do is I want this function to be the one I don't flip and shift. Got it? That's got too much going on. So I'm just going to graph that up here. And I'm going to say if I have tau, and now I'm going to take e to the minus tau times p2 of tau here and graph it. And what that looks like is this. It's simply, and this is e to the minus tau through there. Are you with me, class? Now below it, what I'm going to do is take this function and flip and shift it. Before I do it, I want to take a little time and make sure everybody sees and knows how to draw that functional form. I'm going to do it right here. And I'll flip and shift. This is a typical level of difficulty for a problem that you'd get on a quiz or a test. It requires a fair amount of thought. It's not one of these things you just react to. So if this is going to be versus t here, p2 of t minus 1, where's it centered, class? This function. Class? 1, right? So I come out, this is 1. What is the width? 2. So really it's this, isn't it? It's got a value from 1 to 2 of 1, correct? Everybody see that? Now when I look at this one, I'll call this my, this is the function. Right? This is important. I'm just going to call this one my h here of t, which is equal to p2 of t minus 1. So people get confused with this t minus 1 business. They keep looking at that and they kind of panic when they replace t with what? Tau minus t, or I mean t minus tau, correct, class? They get all flipped out. Think of it, this function h of t is this. All right? With me? Now flip that function, and now it looks like this. Right? Here's 0, here's minus 2, and that would be h of what? Minus tau. Correct, class? You all see what I'm doing here? Everybody? I took the original function, and I simply flipped it around because now the argument is minus tau. Correct, class? But observe, right now, there is already, even when t is 0, this much overlap. Do you all see that? So what we need to do is pull this window this way. Correct, class? Everybody with me? So now when I put the argument here, t minus tau, please watch this. When this argument is t minus tau, I have to ask myself, for what values of t will this thing be dragged to this point, right? Now for t, as t gets larger, greater than 0, at t equals 1, it moves this way. Minus 1 would move this way. Follow me, class? How many see that? So now I'm going to say right here, this is the picture I want you to get in your minds. This is minus 1. The width of this is going to be 2, so this would be minus 3, height 1. And what this is right here is h of, and that would be what? That would be minus 1 minus tau. Do you agree with everybody? That would be exactly when t is minus 1. Correct, class? How many see that? If t was plus 1, it would move the other way. Isn't that right? If t equals 0, then it looks just like this. But now we shifted it by 1 this way. Understand, class? Everybody with me? You can sketch this out at home and go through the thought process of why that's true. Now, we know, therefore, when we look at this, the first point overlap occurs as we're coming from minus infinity would be t equals minus 1. You all see that? Everybody see that? Now just listen to me. Now this window right here, you don't draw this, let me draw. Now this is t, and this is t minus 2 here. This window is being drawn through here, right? Right? And from t equals minus 1 to 1, right? Now this thing gets drawn and exactly overlaps. Isn't that right, class? How many see this? Are you with me? You guys spend time on this stuff because it'll drive you nuts if you don't, you'll flunk. I mean, it'll drive you absolutely nuts, and there's not a lot of partial credit with this either. So now, what happens is, when I look at this by observation, that's t equals minus 1. So you all see that this is the area of overlap. These are how these overlap, correct? Now I have to multiply this function by this function and integrate it to get the convolution of the two, correct? How many see this? Who asked this? You asked that, right? I'm going to do it here. So now I'm going to say for t greater than minus 1, less than 1, the convolution of these two signals, I'll call it y of t, which is just going to be, say, h of t, x of t, convolved with x of t here. That's going to be equal to the integral. Now notice where it starts. Minus 1. Follow me? Minus 1, not 0. Got me on that? That's where the overlap happens. It starts from minus 1 to t of what? E to the minus tau d tau. Do you all agree there? That would be you multiply the two functions, then you integrate them, right? Agree with me? How many agree? With me? These things will challenge you. You have to be on point. You have to spend a lot of time on this, or you will flunk. I'm almost guaranteeing it. So now take a look at what happens when we integrate this. What do we get? E to the minus tau d tau is, go ahead and be formal about it. Isn't it minus, right? E to the minus tau evaluated from minus 1 to t. Isn't that correct, class? All right. Now, what did I tell you to do with a minus sign in front of those? I always say reverse the limits and get rid of it. So this becomes minus 1, this becomes t, and this becomes plus. Do you all agree? Now what happens? That means, this is t. That means, I'm sorry, that's plus. Now that becomes what? E to the 1 minus, right? E to the minus t. Isn't that correct? And that's what it would be for t minus 1 to 1. So this is for t greater than minus 1, less than or equal to 1. Agreed, class? Give me a show of hands on this. Y'all see what I'm doing? What's my next step? Think about what's going on. This is the thing we flipped and shift, right? Now this thing's moving through. When t is equal to 1, it overlaps completely, doesn't it? Correct? Mm-hmm. Now what happens when t is greater than 1? Think about it. When t is greater than 1, what does it look like? This is tau, not t. Remember that. Now when I have this, I have t here. This is still t minus 2, correct? But this would be for t greater than 1. Correct, class? Where's the area of overlap, or where do the functions overlap? Now they overlap from, if you look at this, from here all the way to, class, all the way to 1. Understand? Can you see this? I hope you're understanding when I'm doing this. Y'all understand it? That flip and shift is very important. Yes, miss?
Can you talk about the shift a little more? Like, why do you shift?
Well, you know, when we started, this is the function right here, right? Now, here's what I'm going to do. I'm going to take that out and make it tau, so you can see what I'm talking about. That's tau, right? Now, what would h of minus tau be? Wouldn't it look like this? Minus tau would just be this, right? Like 1, wouldn't it? All right, now add in there t, right? Well, if t is 0, that's it, right? What if t is a little bigger than 0? Now this thing shifts this way. T a little less than 0, it shifts this way. That's what I'm getting at. Very important you do this. By the way, I gave you a JavaScript that would allow you to do these. How many tried that? Did it work? Yes, no, it should work. It works very well, actually. That JavaScript is a godsend. It will save you. I'm telling you. How many tried it? No, Jeff, you didn't try that. That's your kind of deal, right? Computer guy. It is essential that you try that because you can literally take that and draw the functions, any functions, and it'll do it for you. You'll see everything move. You'll see the area of overlap. You'll see the convolution, the actual convolution, the convolution. You'll see the whole thing. Yeah, I'll give you a convulsion a few times. But that's what you'll see. Now, you all see what I'm doing here? All right, now for this part, when is this valid? From T what? Greater than 1, less than, think of the width. From here to here is 2, isn't it? From 1 to 2. Got me? So now what is it going to be? This is true from -1 to 1, but now the convolution would be what? Y of t from 1 to, really? I'm sorry. From t minus 2 to 1. Correct, class? Yes.
I'm confused on how you got t minus 2. I'm confused on where you got t minus 2.
What's the width of this right here? 2, right? So if this is t, wouldn't this be t minus 2? Got me? That's a legit question. If this is t, this has got to be t minus 2, that point. Has to be. Agreed, class? Work with me over here now. All right, now this integration is going from where to where? From t minus 2 till 1. We're integrating d tau. Do you all see that? So what is it going to be? From t minus 2 to 1 of e to the minus tau d tau. That equals minus e to the minus tau from t minus 2, right, to 1. And this is going to be for t greater than 1, less than 3. I'm just putting it there to make sure everybody knows. What's this going to be? Be formal about it. E to the minus t, right? I mean, if you've got a minus sign there, what I'm going to do is go ahead and make that plus. Make this 1, make this t minus 2. If you're all right with that, agreed? Then evaluate it. So you get e to the minus quant v t minus 2 minus, right here, e to the minus 1. And you can expand that if you want. But you all see this, class? Now here's a check. When does this area of overlap go to 0? When t minus 2 is equal to 1. Do you agree? Then the whole, call it the caboose, is now passed through the region of overlap. So t minus 2 equals 1, right? Or what? T would be 3. Do you agree with that, class? So what happens when t equals 3 here? Just look for a second. What do I get? I get e to the minus 1 minus e to the minus 1 or
0.
check, right? That's what it should be. You all see that? Hope I answered your question. These do push your limits of concentration. It'll force you to concentrate more and become a little more attentive to detail, because that's what it's all about. You cannot, if you're a person who gets easily frustrated with detail, you better change your ways, because everything has to do with a lot of details all happening at once. Yes, sir?
So when saying the time balance for like each equation, you know how we have -1, less than t, less than 1? For any of
T greater than minus 1, less than 1. Yeah.
these, right?
Go ahead.
For any of these, do we have like less than or equal to, or?
All right, don't worry about it. I know where you're going with this. In the math department, they're going to give you a lecture about less than or equal to. We're engineers. Less than, equal to, yeah, it's about the same. There is no impulse happening there. It doesn't matter if you put a less than or equal to. It's the same thing, though. All right, we build stuff that you can actually watch. We're not worried about it. They got me on that, class? Oh, don't get me in trouble. All right, with me? Now, are there any other questions? Yes.
Yeah, I have a question on this.
Absolutely, bro.
So, right here on the left, the second graph,
Here.
yeah, how is that one different from the one on the right?
Well,
Because of the T.
it's fundamentally the same graph that just has to do with the time regime. Now I'm saying this right here is for t, what? Greater than 1, less than 3, right? So this point here is greater than 1. So now, out here, this would like 1.5 something, right? Whatever this point is 2 less. Are you with me? Y'all see this class? You see? I don't know if you can see me because I'm always in your way. I hope you understand. Everybody with this? Any other questions about convolution? I have one for you too. I've got to mention one other thing. Anything? All right, now that is continuous time convolution. Briefly, I'm going to do discrete time convolution. And then this is only, I'll give you a few problems with it. I'll show you some tricks later. But this is something the book does not do in this chapter. I wish it would, because discrete time convolution is pretty important. But I don't want to spend too much time on it at this point. Continuous time convolution gives you all the essence of what we're doing. That's the critical thing. All right, now with discrete time, listen to what I'm saying. Now we don't have a value of t, we have a value of n. And generally speaking, you can think of it this way. In discrete time, your x of n, it's usually bracketed. It is for discrete values of n that are integers, 0, 1, 2, 3, 4, so forth. X of n has a single value at that time. A lot of times what they do is say this x of n is really can be found from taking some x of t and just saying t now is equal to n, all right, times some delta t. And that means it's x of n delta t. And then they suppress the delta t and they just say this is x of n. There's a more formal way to do it, but really what we're doing is picking off points of x of t, all spaced by some delta t, that oftentimes is not stated. Understand that, class? It's only stated when it needs to be stated. So now you have this, x of n. Now think about what convolution said before. If I had two functions and I convolved them, if I had x of t and I want to convolve it with h of t, that was equal to an integral from minus infinity to infinity of x of tau times h of t minus tau d tau. That's the fundamental definition of convolution. When we have discrete points, we don't have integrations but summations. That should make sense to you. You all with me on that? So if that's the case, I can say if I have x of n convolved with h of n, in discrete time, really what I'm going to have a sum, and this would be for I equals minus infinity to infinity of x of I times h of I minus n. And that will bother you, but it is essentially the same thing as what's written above, with the integration replaced by a summation. Now remember, that tau is the dummy variable that we integrate out. Now the I is the dummy summation point that we really sum out. Understand that, class? I'm going to do an example of this. How many see this right here? All right, you understand what that is, right? That's an irritating problem.
I have a question about the h. Why is it I minus n instead of n minus n?
Oh, I'm sorry. You're absolutely right. Thank you very, very much. You're absolutely right. It is, sometimes that's okay, but you're absolutely right. That was my bad. The t is like n. All right? Be attentive here. I'm going to do one and show you. Call this y of n, convolution. Now, one other thing before I do this. You know how we define delta t in continuous time as a spike with infinite height, infinitesimal width? Well, with discrete time, not so easy. In discrete time, the delta of n is defined as 1 for n equals 0, and it's 0 else. It simply has a value of 1 when n equals 0. Or when the argument there is 0. It doesn't have to be n. It could be n minus 5. When n minus 5 would be 0. Follow me in that, class? Not infinity. It means the value of that. You know, when you're doing a sum like this, normally if you do an integration, remember, the integral always captures an area of 1 under the delta function. Correct, class? Well, with the summation, it's effectively the same thing. It's capturing that area of 1. It doesn't have a height of infinity now, okay? And there is a u of n. What do you think u of n is? Take a guess. U of n is equal to, it's just like before. Remember, u of t was related to the integral of the delta function, right? From minus infinity to t. You all remember that? Well, here, u of n is equal to a summation. I goes from minus infinity to n of delta here of really what would that be? N minus I. No, of I. What am I saying? Of I. Pardon me. I'm sorry. That's it. Now just listen. Here's what happens. Think about this if n is negative. Right? If we go from minus infinity to any negative value, does this thing ever turn on? We have to go through what point? I equals 0. Now, if n is positive, therefore it's 1 or equal to 0. And if it's negative, it's 0. So u of n is basically this, but it's equal to 1 for n greater than or equal to 0, and it's equal to 0 for n less than 0. That's u of n. It's just like the u of t, only sampled now, isn't it, class? U of t does this, right? U of n is dun, 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 dun. So if you wanted to take a look at the delta function in u of n, here's what they look like. Here's delta of n versus n, 0, 1, 2, minus 1, minus 2. It's just 0, 0, and then right here it goes to 1, then 0, 0. That's it. What sometimes they do, not all books do this, they'll put a little arrow there to indicate that is a delta function. Our book does that for the delta of t in the time domain. I don't know if they do it for delta of n. And then when I look at u of n, now it looks like this. If this is 0, 1, 2, 3, minus 1, minus 2, it's just this. This, then all of a sudden here it goes to 1, here it's 1, here it's 1, here it's 1. You'll see that. You'll see little circles at the top of things. They're called stem plots, I think, in MATLAB. You've seen those before, haven't you, class? Now you all see that's really just sampling the continuous time domain for u of t, right? Isn't it, class? If you just sampled u of t is what? Like that. How many see this? Now we're going to do a simple convolution in discrete time to show you what's going on. And you'll see this. I'm going to do it right here. And I want to tell you, I don't want you to get hung up on discrete time right now. Continuous time has all the essentials. Discrete time is just points in continuous time. Follow me? So, if we take a look at this, suppose I give you two functions to convolve. I give you a function u of n minus u of n minus 2, or make it u of n minus 3. Call that function x of n. And I'm going to say h of n is equal to here, simply u of n minus u of n minus 2. Now, first thing you do is sketch that. What would this look like if it wasn't n, if it was t? U of t minus u of t minus 3. What would that look like? I'm going to put n down here, but it can be just as well called t. What would it look like? Well, it goes, this would be x of n here, but if this was like a t, when does this turn on? 0. So it would be the bing, right? Turns on. And it stays there until 3, right? And it goes to 0. So here's 3. Now that would be continuous time. Agree, class? And I'm just assuming n would be replaced by t. Here's what happens at discrete time. Minus 1, 0, 1, 2, all right. Here I got, for this part, u of n, it's 0, 1, right? 1, correct? 2, it's 1. Remember, this one hasn't turned on. But on 3, what happens? When n equals 3, this one turns on, it goes to 0 again, right? I've got 1 minus 1. Do you all see that? Right. If I have 1 minus, this one turns on at n equals 3. So this is the actual thing. It looks like this. And you can erase this if you want, but sometimes it helps to leave it in. So there's 3 points. It has 3 essential points. But the actual width is only 2, isn't it? Not 3. You all see that? Important difference. So this is my x of n. Now this is my h of n. What does h of n look like? Just think about it. If this was n, this was 0, 1, 2, 3, and I'm graphing my h of n. Think about it. When does it turn on? What, people? At n equal 0. How many see that? Can you all read my writing? You got all quiet on me. Yeah, it's 0. It turns on. It goes to a value of 1, right? What about at 1? Is it still 1? That's 1, that's 0, isn't it? So it's still 1. What about at 2?
No.
No, that's right. This one looks like this. Agree, class? All right. So, think about what you normally do. Find one function that has the most going on and don't change it. This one, they both have about the same going on, doesn't it? I'm going to leave this one as not my x of n, but I'll call it of I. What I'm showing you is this. You all with me? You got me? Now, this is the one I'm going to flip and shift. Are you with me on this one? Everybody see that? First, I'm going to flip it, and I'm going to have h of minus I. So that's what it looks like. Here's what my h of minus I looks like. It's this. By the way, this is now not n, the way I'm doing it. These are I values. Being a little casual with this. But this is now my h of minus I. Do you all agree with me? Please take a look. Have you noticed that this one and this one are at the same point in the end domain at n equals 0? What does the actual equation say? I take this value of x times this value of h of n minus I. So when I should say when n is 0, this is where it starts. Think what happens if we shift this way, if n was negative 1, right? Now there would be no overlap. Do you all see that? So when n equals 1, it's just this times this. That's it. Or 1, right? What about n equal 2? What happens? I mean, sorry, n equals 0. It's this one times this. Pardon me. N equals 0. It's 1, right? What about n equal 1? Now this shifts over by 1, right? Or it does this. And now you see you got this times this is 1, this times this is 1, and we get 2, don't we? We have to add this times this plus this times this, according to that. Do you all see that? Or 2. How many see this? Now keep doing it. What happens when it shifts again? That would be, matter of fact, why don't we do this? N, and we're going to call the convolution, call it y. So n equals 0, it's 1. N equals 1, it's 2, correct? You all see that? How many see this, how I'm doing it? I mean, remember what I'm doing is flipping and shifting through, multiplying each one and adding what's multiplied. Correct, class? All right, with me now. What happens when n is 2? Well, remember that would be n minus I, right? And now would shift over. That's 0, that's 1. Now 2 would shift it here, wouldn't it, guys? I hope I'm not. Y'all with me? Yes, sir. What's that?
I'm kind of confused on whenever you get 0, you get 1, whenever you get 1, you get 0.
Remember when n was equal to 0, right? We had this function and we flipped it. So this point goes here, right? It would be h of minus I, correct? That's when n is 0. Only this point right here is multiplied by this point. All the other points are multiplied together to get 0. 1 times 1 is 1. That's why I put this. I mean, I could go down, I could say for minus 1 it's 0, but if it's not there, it's 0. That's what I'm implying. Okay? All right, go with me now. What happens when it's 2? Y'all agree this is what it looks like, class? This would be 1, this would be 2. Agreed? What's the value?
3.
This times this is 1. This times this is 1. Add them together, we get
2.
2. Again, yes. What about 3? All right, now, let me just do this. I just pull that one off and put it in front. This is what it would look like when it's 3, right? Now remember, point by point. This times this is
1.
This times this is
0.
0. 1 times 1 is 1 or 1, correct? So that means 1. When it's 4, what is it?
0.
Everybody agree with that? How many see this? I'm trying to show you a simple way to do it. Now, I'm not going to go ahead and focus a lot on summations and tricks like that. That's going to come a little later when we do some of the things called Z-transforms and discrete time Fourier transforms. I'll show you a lot of tricks for summations and a way to do that quickly. What I need to do is make you appreciate discrete time convolution is really the same as continuous time, only now with discrete points. Understand, class? Now we're going to go into something that you'll like, I think. I mean, y'all hate convolution, right? Maybe not hate, but you surely appreciate that it's difficult at times to understand what's going on, especially for wild functions. Well, what we're going to do is something we're going to use Laplace transform analysis now to find out how to actually solve a lot of these problems without doing any kind of convolution. Because if you take the Laplace transforms of functions of the x of t and the h of t, you just multiply the Laplace transforms of those two together to get the y of s. And the y of s, we can do the inverse to get the y of t and circumvent convolution. You remember what the strength of the Laplace transform was anymore? Well, before you had differential equations, right, to solve. Y'all remember the Laplace transform? And in the old days, you had to find integration factors and all that other kind of demonic stuff, and you would go nuts, right? At least I used to do this. I had some of this stuff, trying to get the integrating factor for some of it, for your hair. The Laplace transform said, if I take the Laplace transform of the function, for a differential equation, take the Laplace transform of all the terms, I have an algebraic equation. Now I have an equation in S that I can do partial fractions on, and do the inverse of that, and it's trivial compared to the other way. That's the power of Laplace transforms. They simplify the amount of work to solve all sorts of things. Differential equations, convolution, everything. So now we're going to get into Laplace transforms. Unless you have another problem about convolution, but there will always be another problem. Now, how many have had Laplace transforms? You've had it. Haven't you guys had it? Everybody should have had Laplace transforms if you're in here. I don't know who you had or how they explain it. It's one of the most powerful tools mathematically you can have. In electrical engineering, I use this all the time. I use it in radar. I use it in EMC, electromagnetic compatibility. Almost all areas use it. Even digital doesn't use the Laplace transform. They use the Z-transform, which is the discrete time version of the Laplace. And you cannot get away from these transform theories. They are the basis of so much we do in engineering. It also is appreciated greatly right after you do convolution, believe me. So now, here's what the Laplace transform is. It says, if I have a function x of t, the Laplace transform of this function is defined as x of s, and I'll put it down here. And it's defined as the integral from 0 to infinity of x of t times e to the minus st dt, where s itself is defined as some constant sigma that's a real valued function, or real value, plus j omega. The omega is considered the frequency component. Don't get hung up on that now. But it's always lumped down as s. That is the definition of Laplace transform. We're not going to do the inverse right now. That's just the Laplace transform. Are you with me? So the best way to do this, and you've had this before, is do a few Laplace transforms of commonly encountered functions. Let's start with the most commonly encountered function. Suppose I say I have delta of t here. We're going to do a little table. And now I want the Laplace transform of this. So this is going to be the Laplace transform. See? Well, what's the Laplace transform of delta t? Just take a look at this. What would it be? I'll work it right here. X of s, right, would be equal to, now I put delta of t times e to the minus st dt from 0 to infinity. Go from 0 minus here, actually, just a little bit below 0. There's a reason I'm doing it. What's that going to be? When does the delta function turn on? Class? T equals 0. Is that part of the integration? Yeah, because I made that 0 minus. It is. Just a little bit before 0. Understand? All right. Now, what happens? What does a delta t do? It samples whatever's next to it and extracts that value, right? Well, what's e to the 0? 1. Therefore, this is 1, which is nice. You're going to find out why in a bit. So the Laplace transform of delta t is just 1. Now, what would the Laplace transform be of delta of, say, t minus tau? Some arbitrary value. I'm going to put it here. Delta of t minus some tau. Any constant you want. Doesn't have to be tau. You can use that. What's that value going to be? Ask yourself this. When does the delta function turn on?
Tau.
It's t minus tau is 0, or t is equal to tau. Correct, class? Well, if t is tau, what does it do? It extracts the value of any function next to it at that point, correct? How many see that? What do I get? I get e to the minus s tau. That's it. That's it. Are you with me? That's just something, this is all necessary to do. Next, and I'm going to keep coming here. If you hate me because I'm using the same integration kernel, please forgive me. I'm trying to save time. I'm trying not to talk too much, and I know I got a big mouth. So next one I want is u of t. If I take u of t e to the minus st dt, what do I get? Just do the integration. Now I want you to ask yourself logically, what is u of t? What's its value? It's either what or what? 0 or 1. Everybody's like cautious. It's a trick. No, it isn't. I just want some feedback so I know you're there. It's either 0 or 1. When is it 1? For t greater than or equal to 0, or everywhere in this integration, right? Right? With me? So get rid of it. Now what's that integral? E to the minus st dt is simply what? Minus e to the minus st evaluated from 0 to infinity. Guys, what do I do with those limits? Flip them and get rid of the sign, right? What's this? What's e to the 0? What did I forget? 1 over s. I was waiting for somebody else. There's a 1 over s here. Isn't there, class? E to the minus st dt is really what? 1 over s with a minus I, e to the minus st, right? I'm being attentive. I mean, that one was on purpose, but some part. And yell at me. Y'all agree with that? All right, so what's this going to be? It's simply what? 1 over s, isn't it, class? How many see this? It's 1 over s. Some of you remember this, don't you? 1 over s. Now, next one, what happens if I have this function? I bet you most of you get this. What if I have u of t minus tau? Now I've got a time delay. If I have u of t minus tau e to the minus st dt, what's that going to be? Just think about it logically. What's u of t minus tau? It's 0 until I hit what? Tau, and then it is 1. So what can I do? How about I alter that integration to start at tau? Do you agree with me, class? Y'all agree with me? Right? Because it's 0 less than tau, correct? Now, what is that going to be? It's pretty obvious. Now I'm going to have minus, right, 1 over s, e to the minus st, and now here t goes from tau to infinity. You agree with me, don't you? What happens? I change the limits. I always do that. This becomes tau. This becomes infinity. That becomes becomes plus. Agreed? So this is going to be 1 over s times e to the minus s tau. And then it's minus e to the minus infinity, which is 0. Do you understand that, class? I don't even bother writing that. So this is really going to be 1 over s e to the minus s times tau. We're starting to populate a table. It's important to see this. Now, I usually go and do the next one. I want to look at my book for 1 second before I do this. This is the next chapter in your book, chapter 3. And I didn't talk about causality, but I'm going to in 1 second talk about it. I mean, you've had Laplace transforms, so I'm being a little more casual about this than usual. Let me do one other thing and then I'll finish with causality. If I have e to the minus at times u of t, and I want the transform of that, the Laplace transform, what would it be? We'll go here. That's the definition I put in from 0 to infinity e to the minus at times e to the minus st dt, correct? Now, how do you do that integration typically? If you have e to the a times e to the b, isn't that e to the a plus b? You agree with that, class? So I'm going to group the exponential terms together, and I can say this is really going to be the integral from 0 to infinity here of e to the minus quantity a plus st dt. And what will that be? Isn't that going to be minus 1 over s plus a times e to the minus quantity a plus st evaluated from 0 to infinity, class? Do you agree?
Yeah.
And you know I'm going to do the old switcheroo with the limits to get rid of that negative sign and then evaluate it. So this is simply going to be what? 1 over s plus a. Isn't it, class? Class? Now, how many of you remember seeing this stuff before? All right, you may not have seen the delta function or the u of t, but you've seen the rest of it. At least you've seen the e to the minus at, didn't you? I'm going to go through next time more on the Laplace transform. We'll get a quiz next time. Now, hear me. I want you to do the Laplace transform homework along with being ready for the convolution quiz, all right? Because I just might ask something about one of these, just to make sure everybody's been doing what I ask. One other thing, too. If you need to see me about something, let me know. I'll be in my office right after class. I have a cajillion meetings right now. I mean, I get stuck in meetings out of the blue. Somebody will call me at 8 in the morning. They need me to see me at 9. Why? Oh, I can't tell you. And I can't go. No, you got to go. Okay. But I'll meet you anytime. And right after class, you can meet me. You need to see me. Can you see me after class? Most of the time, people want to see me after homework, right? So if you want to see me like on Thursday or Tuesday, like tomorrow, I'm usually about 12 to 12:15. I get back there in my office. It depends when the guys get back from lunch. And I'll be there as long as it takes if you're there, okay? And I'll try to help you as much as I can, too. Causality in a nutshell. Just listen, you'll like it. In the real world, what happens about cause and effect? If there's an input-output, the output can't occur before the input. Do you all agree with me?
Yeah.
All right? Well, if the output can anticipate the input, that's called non-causal. That would mean it knows that beforehand something's going to happen at t equals 0, so at t equals minus 5, something's already happening. That would be anticipating, like prophecy and stuff like that. You can't do that in the real world with real systems. It's called non-causal behavior. However, we'll talk more about that next time. And y'all, have you heard of causality in some of your classes? Psych and stuff like that? No? Well, cause and effect. Something causes something, the effect happens at that time or later. You can't have something that knows something's going to happen and it already does something. That would be predictive or anticipating it. You can't have it. That's non-causal. You'll see why this is so important in a little bit. Anyway, I'm just telling you, that's non-causal. We don't deal with non-causal systems because they're fictitious. They don't exist.